Have you ever felt like geometry is just this huge list of random rules you're supposed to memorize for a test? Well, what if I told you that a ton of the shapes you need to know are all part of one big connected family? In this explainer, we are going to crack the code on that family's secrets. And trust me, it's going to make geometry proofs a whole lot simpler to figure out.
So, to get started, let's kick things off with a little puzzle. You've seen squares, you've seen rectangles, and you've seen rhombuses a million times. But what's the real connection between them? You could even pause and think about it for a second. What's the one thing they all share?
If you guessed that they're all related, you are absolutely right. The best way to think about it is like a family tree, but for shapes. You've got this one common ancestor at the top, and it passes down its key traits, kind of like its DNA, to all the shapes that come after it. So here's our game plan for today. We're going to start by meeting the head of this quadrilateral family. Then we'll get to know its pretty special kids, the rectangle and the rhombus, and even a grandchild. After that, we'll shift gears to the building blocks of geometry, triangles. And we'll wrap up with the ultimate toolkit for proving they're identical.
First things first, the quadrilateral family. And look, understanding this hierarchy, this family tree, it's not just some random trivia. It's really the secret to mastering all their properties without just trying to memorize 100 different rules. So, sitting at the very top of this family tree is the parallelogram. This is our OG shape, you could say. Its properties are the family's core DNA, and they get passed down through every single generation. If you can master the parallelogram, you've basically learned the rules for the entire family. Okay, so what is this core DNA? Well, there are 4 rules that every single parallelogram has to follow. No exceptions. Opposite sides, they're parallel and congruent, meaning they're the same length. Opposite angles, also congruent. Consecutive angles are supplementary, which is just a fancy way of saying any 2 angles next to each other add up to 180 degrees. And finally, the diagonals cut each other perfectly in half. These 4 rules are our foundation.
All right, now it's time to meet the kids, the special parallelograms. They are just like their parent. They inherit all that core DNA we just went over, but each one has its own little superpower that makes it unique.
First up, we've got the rectangle. It's a parallelogram, so it has to follow all those family rules. But its superpower is its angles. All 4 of them are perfect 90-degree right angles. And as a cool little bonus, its diagonals are the exact same length. Think of it as a parallelogram that's been neatly squared up. Next, let's meet the rhombus. Now, it's also a parallelogram deep down, but its special power is all about its sides. All 4 of them are exactly the same length. And it has another really cool trick. Its diagonals are perpendicular, meaning they cross each other at a perfect 90-degree angle. Okay, so we've got the rectangle with its perfect 90-degree angles, and we've got the rhombus with its perfectly equal sides. So what do you think happens when we smash those 2 superpowers together? Just picture it. You take the 4 right angles from a rectangle, and you combine them with the 4 equal sides from a rhombus. What amazing shape does that fusion create? You get a square, of course! The square is basically the superstar of the family. It's like the grandchild that got all the best traits from both of its parents, the rectangle and the rhombus. It really is the whole package. And this right here is the biggest takeaway. A square isn't some totally separate thing. It is a rectangle because it has 4 right angles, and it is a rhombus because it has 4 equal sides. It's the most specialized shape in the whole family, with the most properties of all. All right, so we've pretty much mastered the quadrilateral family. Now let's zoom in on the building blocks of all these shapes, triangles. I mean, think about it. If you draw a diagonal line in any quadrilateral, what do you get? 2 triangles. They are literally everywhere, and you have to know them for proofs. This table gives you a quick breakdown of the 3 main types. The scalene triangle is kind of the wild card. No equal sides, no equal angles. An isosceles has a little more order to it, with at least 2 equal sides, which means it also has 2 equal base angles. And then you've got the equilateral triangle, the total perfectionist. All 3 sides are equal, and all 3 angles are equal, with every angle locked in at exactly 60 degrees. And now for the main event, proving that 2 triangles are congruent, that they're identical copies of each other. This is where a lot of people get stuck. But here's the secret. You don't need to prove that every single side and every single angle matches. You just need to use one of the 4 power tools in your geometry toolkit. Tool number 1 is side, 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 or SSS. This one is the most straightforward.
If you can just show that all three sides of one triangle are the exact same length as the three sides on the other triangle, you're done. That's it. They are guaranteed to be congruent.
Tool number 2 is side angle side, or SAS. Now for this one to work, you need two sides and the angle that's between them. Think of it like a sandwich. The angle has to be the filling squeezed right in between the two sides. If that little sandwich pattern matches on both triangles, they're congruent.
Next up is angle side angle, ASA. This is basically the reverse of the last one. This time, the side is the filling in the sandwich, locked between two angles. If you can prove that this pattern, angle, then side, then angle, matches up, the triangles are definitely congruent.
And our final tool is angle angle side, or AAS. This one actually breaks that sandwich rule. Here you prove two angles and a side are congruent, but the side is not between the angles, it's on the outside. But as long as you've got two matching angles and one matching non-included side, you're golden.
So, why do we even care so much about proving triangles are congruent? Well, it all comes down to this one pro tip, CPCTC. It stands for corresponding parts of congruent triangles are congruent. Basically, once you've used one of our 4 tools to prove the triangles are identical, you can then claim that any of their other matching parts, sides, or angles are also congruent. This is the master key that unlocks the final step in so many geometry proofs. So next time you see a complicated problem, just ask yourself, where are the triangles, and which tool can I use to prove they're the same?